Okay, I think I'm live now. Okay, so hey guys, welcome back to another Micromouse meeting. First meeting that I'm going to be recording this semester. Let me stop Spotify. Why do I still have Spotify on? Okay, so yeah, this is going to be the first recorded meeting of this semester. And what better way to start off than to start off with the main component of our bots, the motors. So yeah, let's get right into this. Motors used in Micromouse. Okay, so some basic things that you should probably know about motors. So motor basics. Electric motors, they typically operate by the interactions that take place between the electric current that go through the wire coils and a set magnetic field via like magnets that are installed in the motor. And yeah, the interactions between those two things make the motor rotate, or rotor rotate, not the motor itself. So its main parts, the main parts a motor, any electric motor typically consists of, are the stator, the rotor, and the coils. Okay, the stator is the stationary part typically in your motor, whereas the rotor is the rotating part. Um, and the design varies between each different type of electric motor, and we're going to be covering three different types. We're going to be covering brush DC motors, brushless DC motors, and stepper motors, which can be considered AC motors, even though you get your power for the for the stepper motors from a DC power source. They're still considered alternating current motors. I'll get into that as we go on. Yeah. Brush DC motors. There's a little diagram there depicting how it works. You have your stator, basically, which in this case is two pole magnets, your stator magnets right there. And you have your motor, you have your rotor, which is wrapped in coils. And on the ends here are some metal pieces, right? And as the current flows through those coils, the magnetic field on these metal pieces alternate, and that's due to the commutator, because as it rotates, right, commutator comes in contact with these two things called brushes. Now, the brushes are where your power is coming from to your brush DC motors. Uh, the brushes are typically connected to prongs on the outside of the motor, as you can see here. I don't know if you can see my mouse. Should be. I think you are. So these prongs connect to the brushes, right? And this is where you would typically connect your power terminals to in order to power the motor. Now, current is going to go through these brushes, from one brush through the commutator and to the other brush. And as this happens, the rotor, right? The metal pieces on the rotor, they're going to generate a magnetic field, and that's going to interact with the stator, which is going to either repel it or attract it based on how the magnetic field is oriented. And because of that, it's going to spin. Now, if you reverse the current here, this rotor is going to spin the opposite way. And we'll get into how that works and how we can manipulate that when we get to motor drivers. But right now, let's go over what motors are we specifically going to use. So yes, we will be using brush DC motors. Typically, brush DC motors are not considered like the most power efficient, and you also have some concerns of uh, durability issues, which we're not really too worried about because we're not dealing in any large scale industrial applications where that would be that much of an issue. And honestly, brush DC motors and brushless DC motors at this scale, it's fine. It wouldn't make that much of a difference. Brushless DC motors, as you can see, the coils, right, they don't come into contact with anything. or there's no brushes to like come into contact with anything. The coils are actually here, wrapped around the stators instead of the rotors this time, right? The rotors is what's going to be housing the magnet, and the stator is going to have the coil wrapped around it, and its magnetic fields are going to be alternating in order to make the rotor spin. So this is how brushless DC motors work, according to this diagram right here. These are also, by the way, brushless DC motors. They're similar to the next type of motors we're going to be discussing as well, but they're not quite as accurate because their steps aren't like fixed. Um, this rotation is just continuous. It's not like stepper motors, as we'll get on into later, but they are very similar. Uh, if you look at the following diagrams. Okay. So yeah, as I said, stepper motors, they work in a similar fashion. You know, the coils are going to be wrapped around the stator uh, metal pieces, and that's going to create, you know, alternating magnetic fields in order to rotate your rotor. And your rotor is going to have a permanent magnet. You know, its magnetic field is not changing. It's just rotating based on what the stator is currently like. Okay. Any questions up to this point? I hope I explained everything here
Not yet.
clearly. Okay. So yeah, we're going to be using these. We're not going to be using brushless DC or steppers. Uh, Steppers specifically, I don't think are too useful for us because we don't need to keep track of position with our motors. We're mainly concerned about speed. And while steppers are also fine for keeping track of speed, there can be issues with how do you say, the rotor accidentally skipping a few steps because, you know, if it's spinning at a high enough speed or there's a bit of load that it's trying to carry, and when you like stop, it could skip a few steps, and that could just throw off your whole measurement. Next part, magnetic encoders. Okay, uh, these are going to be used to essentially keep track of how fast our motors are rotating, and they use a little something called the Hall effect. So in the Hall effect, you have your power source here, you know, you have your circuit here, and just assume this is like a conductor of some sort of like metal plate or whatever, right? If you were to, let's say, have a magnetic field that's above this directly, what that magnetic field is going to do is that's going to interact with the current flow that's going across this plate, and it's going to push the electrons to one side of the plate, right? So it's going to distribute charge to two sides of the plate. That's how this effect works. And why that's useful for Hall sensors is that it allows us to determine, okay, how has this magnet rotated, right? So you can have two Hall sensors here. Let's say you have your North Pole here. It's going to push the electrons to one side of the Hall sensor, right? And it's going to read a digital high because they're going to one side. Okay, so let's say this rotates a little bit, right? And it goes to this Hall sensor instead. So what's going to happen there is that this Hall sensor is now going to read high, and that Hall sensor is going to read low. Okay, and then so on and so forth as it keeps rotating between the two poles. It's going to give you different signals on each of these, and with those signals you can tell which direction the motor is rotating, and based on the frequency of these waves you can tell how fast it's rotating. This is a bit more complex topic to discuss, like exactly how um, this Hall effect works. It's more clear if you learn it in physics. I think physics 2 goes over the Hall effect and uh, currents and how magnetic fields interact with uh, electric currents and whatnot. So, okay, And this is what it looks like, the sensor we're going to be using. So as you can see, there's, the encoder we're going to be using. So as you can see, there's two Hall effect sensors here, and they're positioned right below the magnet. It's going to be attached to the shaft behind this motor, the brush DC motor we're going to be using. So the encoder is going to go on the shaft first, and then you put in the magnet. And then as that magnet rotates, these two Hall sensors will detect, oh, okay, it's spinning this way, or it's spinning that way. Or it can say, okay, it's not spinning at all. Let me turn on my cam. Okay. So yeah, as you can see, you have your encoder there. Right, this is the I'll take it apart. I'll take the magnet off. I can't take the encoder off. The encoder is actually soldered onto the motor. As you can see here, this is how the back looks like. These two holes are. How am I going to set this up? Okay. This hole right here. Come on. This hole and that hole. That's where the power terminals are for the motor. That's what connects to the brushes, and basically you place those two prongs into these two holes and then you solder them. So this is now secured in place. What you do afterwards is you have to make sure these Hall effect sensors are facing out like this, so that when you put the magnet on, they'll be actually able to sense the magnet. I have accidentally done it backwards sometimes. Okay. Okay, there we go. Yeah, that's what it looks like. And just to give a little demo of how this would work, you have to take, if you can see the markings on these encoders, M1 and M2 correspond to the power that's going to be going to the motor. So M1 and M2 are going to be like connected to these two holes right here, and then power is going to go through that into the motor. GND and VCC do not go to the motor. GND and VCC are actually power for the sensors themselves. So the power supply for the motor and the sensor are going to be separate. That's pretty obvious if you think about it, because motors use 12 volts of power. The sensor only uses like, I think at max 5 or 3.7. I don't know if it has a step down mechanism thing or whatever. I think it only takes in 3.7. And then it also has output signals for both of the encoders. So, this could be encoder A, encoder B, doesn't matter. It's going to give the output signals of whatever the sensors are reading. And it's going to output it through these channels. And these channels are going to be connected directly back to your microcontroller so you can use the readings. So I'm going to attach M1 and M2 to a battery. Connect that. Okay, so if I do it like this, typically shouldn't keep your motors on full power all the time. As I said, the brushes do come in contact with the commutator, and if you run them on full power all the time, those brushes are going to wear out. Again, these are decently well quality motors, so they won't wear out easily, but do keep it in moderation. Okay, moving on. The motor driver. Um, the motor drivers we're going to be using use a topology known as H-bridge, an H-bridge circuit. And we're going to be using PWM signals to control the speed of these motors. Okay, so what is an H-bridge? Okay, this is essentially an H-bridge. An H-bridge has 4 switches, and these switches control how the current is going to go through your motor. If all the switches are open, there's going to be no current flowing through your motor. It's going to be off, right? Uh, if you want your motor to spin in, I think this will make it spin clockwise. If I'm not mistaken. Pretty sure. So if you close these two switches, it doesn't matter. If you close these two switches, uh, switch 1 and switch 4, the switches diagonally across from each other, motor is going to spin in one direction. And then if you open those switches and then close switch 2 and switch 3, motor is going to spin in the other direction. One thing you should remember, you don't have to worry about this, but because the motor driver we're using is going to take care of it. But do keep in mind, don't close switch 1 and switch 2 at the same time, because that will short your circuit. Again, our motor driver has protections against these. Has protections against back EMF, which is generated by, let's say, if your motor is running, and then an outside force moves it. It's going to generate a back EMF, which could lead to a short circuit. Because typically, if you have a power source and then other power is coming into your system, it does not end well. Same thing with here. These two switches should not be on at the same time or closed at the same time. You could close all 4 of these at the same time, but again, that would create another issue. Similar to what would happen if 2 switches on the same side were closed. So yeah, why is this important? This is because we can actually control these switches via our microcontroller. Right? It could send a command to close these 2 switches so that our motor spins one way, or it could send a command to instead close these 2 switches so our motor runs the other way. Or it could just open all the switches to make sure that the motor isn't receiving any power, so the bot can stop. So how exactly would we control the speed? Speed is going to be controlled by how frequently we are sending out power to our motors. And that is managed via something called pulse width modulation, or PWM. So what these signals do is they send out a electrical high, or your max signal to your motors uh, in in set periods. So for a 0% duty cycle, this would be equivalent to a statement of code saying analog write 0. Your motors aren't getting any power, your motor is going at a speed of 0. And then let's say you want your motors to spin a little bit faster, but not at max speed. You would increase it up. So let's say, what does it say? Your 25% duty cycle, right? So it sends out the electrical signal in short pulses to gradually move the motor. And then these electrical signals eventually become greater and greater in terms of their pulse width, until eventually you get just like a continuous electrical high, and that's basically telling your motors to go at full speed. And you can see here how it's described. This is your period before you start you send out your next PWM wave, and this is your pulse width to manage how much power you're generating or how much power you're sending out to your motor to control how fast it goes. Okay, so this is the motor driver we're going to be using. This is how it looks like. I can show it right now, actually. Ooh, okay. Yeah, so this is how the motor driver looks like. It's the TB something. I don't remember the full name. TB6612FNG, I think. Oh, not there yet. And this motor driver, you're gonna notice it has a couple little words there written. PWMA, AIN1, AIN2, STVY. Um, so the one on my camera right now, the left side is basically going to be your inputs from your microcontroller. PWMA is going to be the PWM signal your microcontroller is going to be sending out to tell how fast your motor should go. AIN1, AIN2, and AIN1, those correspond to the H bridge that I was talking about earlier. They're going to correspond to this system right here. So let's say you set both AIN1 and AIN2 to low. That's going to say that, okay, all these switches are open. Okay, then let's say you set AIN2 to high and then AIN1 to low. Let's just say AIN2 corresponds to S3 here. S3 and S2. So if you set AIN2 to high, that's going to close these two switches. And then AIN1 to low, it's going to keep these switches open. And then do vice versa, your motor is going to spin in the other direction. Right, so those are going to control your direction. PWM is going to control your direction, and then the in1 and in2 switches you're going to control. Did I just say PWM is going to control your direction? I meant speed. I don't know what I'm saying. In1 and in2 are going to control your direction. Okay. And also on here, you see the right side, which has, well, in the camera, in the PowerPoint, it shows the labels here, which is weird. I don't know why they make it so that you have to solder it so that when you place this thing down on a breadboard, it's going to be upside down. You can't see any of these labels. I don't know why they solder it like that in the picture on the store page. I prefer to solder it so that this side is facing up instead of this side. Just makes everything more clear. So basically GND, VCC, AO1, AO2. That side is going to be your output to your motors. So AO1 and AO2 are going to be the current running to your motors. So let's say AO1 is high, it's going to carry a certain PWM signal that's going to be controlling your motor speed, and AO2 is low. It's going to say, okay, so AO1 is receiving a signal, AO2 is low, so this motor is spinning clockwise. If it's the other way around, it's going to spin counterclockwise. Oh yeah, another thing you may have noticed, there's A and B here. So this motor driver actually can control up to 2 DC motors, brush DC motors. If you're using a stepper motor, it can only do one. That has to do with how you power stepper motors, and due to the fact that they're AC. That's a bit more complicated, so I'm not going to cover over that. Essentially, the motor driver we have right now, it's good enough to power 2 motors.